Thank you, Dilpreet. Thank you for arranging all the logistics for this event to happen. So first, let me start my video. So, am I visible to all?
Yes, Gaurav, you are visible.
Okay. So, good evening to one and all. So, welcome to this lecture series, and especially in the session which is going to be taken by me. And basically, in this session, we'll give you a brief idea about the applications of linear algebra, more precisely in image processing. However, so the title says that application of linear algebra in image processing. However, I am going to talk about some more applications as well if time permits me, maybe at the end of this particular session. Dilpreet, I think 7 or 8 people have joined. So should we wait for some time or we
Yeah,
will
you
start?
can minutes, but it is okay.
Okay.
Yeah.
So let us wait for a few minutes. Let's say 2-3 minutes for other persons to join, and then we will start discussion on the applications of linear algebra. So in the meanwhile, let me share my screen so that if you are able to see that, you can always let me know. So is my screen visible?
Yes, Gaurav, it's visible.
Okay. So Dilpreet, I think it's already 5:30. Can we start or is?
Yes, we can start.
Okay, so maybe the person who are missing, they will join in between. Okay, so good evening all. So let me start this journey of the applications of linear algebra. I hope that you have enjoyed this whole activity of TEW because I think this is going to be the last session for the TEW activity, and then you are going to have a very a nice insight of the linear algebra where it can be useful, or where we can use it for different kind of purposes. So in my presentation, and this 3 or 4 presentation which I am going to have in these lectures, I will try to give you an overview how the linear algebra is going to is going to help us in understanding the different real life phenomena, as well as the different applications where we are going to use the linear algebra, or even in our daily life, if we are going to where we are going to use this linear algebra concepts, or maybe even you can say in our elementary education which we have learned so far without linear algebra, how linear algebra can is going to affect or enhance that the visualization of those things. So let me start this session with a very simple question to all of you: what is linear algebra? And I hope that all of you are going to have a very nice and clear answer of this particular question. So anyone want to give me a very brief answer to this question? What is the linear algebra? Anyone who want to speak, please unmute yourself and you can speak. And whenever you are not speaking, you can definitely going to unmute yourself. Oh, sorry, mute yourself. So anyone want to shed some light on this particular word, linear algebra, which we are going to have written on this particular slide? So anyone? Okay. Okay, so let me start discussion. I think people are hesitant to say something, but anyways, if I look at this word linear algebra, then suddenly there are 2 different words comes in my mind, and I say that linear algebra is nothing but the combination of 2 words. One is called linear, other one is called algebra. So when I try to define this linear algebra using these 2 words, linear and algebra, then definitely the meaning of this particular word linear algebra comes out when I know the meaning of linear and algebra. And these are the 2 most common terms which we are going to use throughout the mathematics. Doesn't matter what in which uh, program we are having. These 2 words we are frequently used. Even from our elementary education, we use the word linear and we use the word algebra as well. So now let us try to understand what is the meaning of these 2 words. So when you talk about algebra, so the meaning of algebra is roughly the relationship. So now you can understand that when we talk about the relationship, then in order to find out relation, we should have more than one entity in our head. And when we talk about algebra, so basically we are looking at the relationship among the numbers. So now, like I will take a very simple example over here, just to explain why I'm saying the algebra means relationship. Let me take x plus y whole square is equal to x square plus y square plus 2xy. Everyone knows this is a very beautiful identity which we are using from our childhood. But whenever we try to prove this kind of identity, we never talk about the numbers. Of course, this x and y are going to be numbers, and then this entity or this identity is going to be proved. And but whenever we try to prove it, we are just going to prove this identity without the numbers. And that is the beauty of algebra, where you want to find out the relationship between the 2 things or 2 numbers, even without knowing those numbers. And that is why when I said that algebra, whenever we talk about algebra means the relationship. So it's going to be very simple simple definition, or the simplest definition of algebra, where you just want to exploit the relationship. And relationship is going to be of any kind. It's going to be linear. It's going to be non-linear. Now this word linear comes when we talk about the linear. Then the meaning of linear is roughly you can say the line-like. Basically, we are looking for the analysis of the straight lines, because when if you go to your elementary education, the linear word which you are going to use first time, that is with respect to the lines. So linear means we are just looking for the line-like structures which we are going to have across us or around us. And when you try to combine these 2 things, linear and algebra, algebra says I'm trying to exploit the relationship. Linear says I'm just trying to find out the lines or the line structure. Then when you combine that, then the linear algebra roughly says that I just want to exploit or find the line-like relationship among the different entities. So now when you talk about a line-like relationship, the first extension from algebra which you come to know is that now numbers are not going to work for me. Now I need to think beyond the numbers. And whenever you try to think beyond the numbers, you are looking at the collection of numbers. Now, whenever you try to find out the collection of numbers, then there are different modalities for doing so. Someone says, I will form a set. Someone say, okay, I don't want to form a set. I just want to exploit a particular relationship between those numbers which are given. But in any case, whenever I try to take the collection of numbers, the easiest and the simplest extension of a number is going to be called the vectors. Let's say x, y, or maybe x, y, z, and so on. So whenever you talk about linear algebra, you are just thinking of going away from numbers in the sense of you are now going to take a collection of numbers in the form of vector. And that is why whenever you talk about linear algebra, the first and the basic things comes in your mind is vector spaces. So now again, this is going to be a very long story how this algebra and linear bring together a new flavor of vectors where you are going to just play with the vector. You can add vector, you can multiply vector with some scalar, and then try to see what are the different effects of that particular vector on those particular operations. Now, if you are not even satisfied with this particular concept called vectors, then what will happen? Then you are saying that in order to come from number to vectors, I have taken the collection of numbers. And when you want to go beyond the vectors, then you can say, I want to take the collection of vectors. And whenever you try to take the collection of vectors, what you are going to get. So it's all about how you are going to arrange those vectors, either in a row manner, in a horizontal manner, or in a vertical manner, or the column manner. You are going to get another extension which is called the matrices, where you are going to have a vector v1 as a first column, then v2, and so on to vn. So now this is a very simple extension where whatever the basic information you know from your elementary education, that's number in mathematics, you are just going to exploit or extend towards the vectors and then matrices. And then whenever you say, okay, now I just want to take the collection of matrices, then you are going to have the tensors into the picture. So the next stage in this particular extension is going to be the tensors, where you are going to have the collection of matrices of same size or the similar size, whatever it may be. It may be homogeneous, it may be heterogeneous. So whenever we talk about the linear algebra, it's all about vectors, matrices, and beyond. So however, in our education system, we always go till matrices, and rest of the things are for the research purposes. So whenever you go for the higher education, like the doctorate or maybe beyond towards the research side, then you have to extend the concept of matrices for the concept of tensors, so that you are even going to exploit the different properties of the high dimensional space. Because if you closely look at in this particular extension, as soon as you are taking a collection of the basic things, you are trying to increase the dimension you are working in. And when you talk about tensor, the meaning is the dimension is beyond 3, and most of the times you are going to have n-dimensional space for which you can use for the different purposes. So when you talk about the applications of linear algebra, then you have to find where I am going to use these vectors in the real life applications or different applications, where I want to use these matrices, or where I want to use these tensors. So now the uses of these entities will lead to the application of linear algebra. So, so the general statement which I want to give at the end, the application of linear algebra generally focuses on the implications of matrices, determinants, and vectors. Again, I am not including the tensor word over here because if you want to utilize this tensor, then it is very hard to visualize because the dimension is generally is going to be very high. However, you can also utilize these tensors into the picture or into this particular statement. So now I have used the word determinant over here, which is actually obtained from the matrices. So this matrices and determinant, you can say, is going to be a single unit. But I want to emphasize this determinant because in most of the phenomena where I am looking for a single value, then matrices is not going to give me that single value, and then immediate extension or the property of matrix which will give me a single value to utilize is nothing but the determinant. Of course, determinant is going to have their own restriction, like it is going to happen only for square matrices and so on and so forth. So again, I'm not going into the technicalities right now, but this lecture will go on, we will try to discuss all those things as well. But in general, if you talk about the applications of linear algebra, I'm basically talking about the vectors, matrices, and a similar kind of structure such as tensors. Okay, so now let us quickly talk about the connections of linear algebra in our daily life, or maybe whatever elementary education we are having, or our country is giving. So in the linear, you can find the diverse application of linear algebra. In fact, I can say that linear algebra is everywhere. So the simplest example, which from the geometry of the class 9th student, which can relate, is called the finding the centroid. Now, even the finding a centroid, we can use the concept of matrices in the form of determinant. In fact, the area, like the area of a square, area of a triangle, area of you can say of any shape or of any general shape. Again, we can utilize the matrix theory or the linear algebra into it to get the areas and to give a new visualization or representation of these things. Even we can use this finance in the finance as well. Now, when I say finance, so I'm not going to the financial mathematics at all, because this is going to be the high level altogether, high level concept. I'm just talking about the interest, the compound interest, the normal interest, all those things. So in those cases we can use the linear algebra. Then of course in the geometry, though I have taken the two very basic concept from the geometry separately, but apart from these two, there are a few more examples or the situations where the matrix theory plays a very critical role for that particular problem. Now, the last thing which I want to take in this particular list is nothing but the solving simultaneous equations. And I know that everyone is aware of how to solve the simultaneous equations. So it's like when you look at the competitive examination, they are going to have different kind of questions for the kids, like the two bagels and the two toffees are going to be 25, and the price of one bagel and two toffees is going to be 16. Then what is the individual price of these things? So these are the very elementary questions which are actually meant for the small school kids to understand how you are going to use mathematics in your daily life to achieve certain assumptions or certain observations. So now let me devote a few slides on these 5 topics which I have mentioned over here, and then we will directly jump to the high level applications of linear algebra. So now centroid, again, as I mentioned, that you have to find out the center of gravity of any function, that is called centroid in the mathematics. So if I look at this particular, if I consider this particular object or the shape, and I just want to find out the centroid of this, then I know that I am going to, in the geometry, I'm going to have some formulation for this particular finding of this particular centroid of this particular shape. However, if I want to utilize the linear algebra, how the things is going to be done. So now I will assume that this point is going to be the origin for me, and then assuming this as the origin and the corners of this particular shape, I can always define a vector. So it's not nothing but a vector 6, 0. This is nothing but a vector 6, 4. So basically what I'm trying to do is I'm just taking the corner and I'm just assuming one corner as my origin. You can take any corner, it's up to you. Because in this case, when we talk about this area and the thing, then there are going to be the positive quantities most of the times. So it is not going to make much difference. So, but again, the lower part is going to, if you take a lower corner as the origin, then things is going to be in the positive direction. So it's everything is going to be fine. So now you can always find out this particular vectors over here, which is nothing but the corners of your shape, and then immediately you can take the average of these vectors to get the centroid. So this is again going to be very simplest way to find the centroid of a particular shape. Again, you can verify the centroid of this particular shape if you want to utilize the basic geometric formula which you have. So that is that maybe I may leave as a small homework for you for this particular activity. So now this is for the centroid. Then let us try to extend a little bit further. Then let us talk about the area. So now how to find out the area of this? So if I assume that since all these boxes are square, so let me say this is going to be a unity square, then I will just count all the squares, sum it up, and I will get the solution. So this is going to be the simplest way to solve it. And I am going to have the 36, not meter square is going to be the unit square because I don't know what is the unit. So it is going to be the unit square. So whatever the size of a single element over here, that will give you the basic idea. Now, if I want to solve this problem using the linear algebra, then again I have to take help of vectors. So again, as we did in the centroid, just try to take one point as your origin. Try to find out the vector representation of that particular shape, and then try to find out the area. Then how to find out? You can look at in this particular shape. I am going to get a triangle. This triangle, this triangle. This is again a triangle. This is again a triangle, and this is again a triangle. So the idea behind it, I just want to find out the area of this triangle, this particular triangle, all the triangles, and then sum it up to get the final solution. So now I hope that all of you are aware from the vector calculus, and then using the vector calculus, you can immediately identify what is the area of a triangle. So let me give you a very brief idea about it. Let's say I'm going to have a vector x, and then I'm going to have a vector y with me, and I'm just looking for the area of this particular triangle. Then what I will do, I will take another vector which is parallel to this, again take the parallel to this, and then using this particular parallelogram law, I can always find out the area. So the area of this parallelogram is say A, then the area of triangle. The area of triangle is nothing but 1 by 2 of the area of parallelogram. And the area of parallelogram can be easily identified by the cross multiplication of these vectors. So again, when you try to extend this particular concept over here, then you are going to get the area of this shape even with this particular simple formula, and then you are going to get the same solution which you are going to get from the previous solution, previous case. So even in finding out the areas of certain shapes, the linear algebra is going to give you a very nice overview to get the solution. So this is another going to be very simple example in which you are just about to find out the area of a triangle. Area of a particular shape using the linear algebra. So now let us take a very simple example from the finance as well. As I mentioned that I'm not going in the higher terms in the financial engineering at all. So let us take a very simple example of compound interest. So how this the linear algebra comes into the picture over here. Let's say I'm going to have the 3 different saving schemes with different interest rate, which is going to be compounded annually. Let's say these are going to be the 3 different rates for that particular schemes which I am having. Then I can immediately identify the total compound, or you can say the amount after the compound interest using this particular formula. Let me give a very brief discussion or the gist of this particular formula. So if you recall the definition of the compound interest is going to be A is equal to P multiplied 1 by R over M whole power T, where T is nothing but the time, M is nothing but whether the interest is going to be compounded 1 time, 2 time, 3 time in a year. So it is nothing but the number of times you are going to get the interest. This is going to be the rate, this is going to be the principal amount, this is going to be the compounded amount which you are going to get after this particular time t. So now for my simplification, I will say that the time is going to be 1. I am just going to take the 1 year, and I will say that the interest is going to be compounded once only throughout the year. So M is again going to be 1. So in this case, whenever I take these two assumptions, then this formula will lead to the A is equal to P 1 plus R to the power T. So now if you look at this first row and the first row of this, then what I'm trying to do over here is I'm just trying to compile the amount which I'm going to get with respect to the first scheme in the first row, second scheme in the second row, and the third scheme in the third row. So this is again going to have an arrangement where I am going to utilize the concepts of matrix or the linear algebra for the finance in the finance sector, especially in the compound interest. So it may also possible that the linear algebra is not directly involved or included in a certain application. However, you can take certain assumptions so that the linear algebra concepts are going to be applicable in those scenarios. So this is one of the this is going to be one of that kind of scenario where you can mold everything yourself or towards the applicability of the linear algebra. So this is a very simplest example. Now you can even take the example of the simple interest or maybe some typical compound interest problem as well, where these assumptions are not going to be there. Still, you are going to have the applicability of the linear algebra in those cases as well. But for the simplicity, I'm just taking a very simple example in my slides. Now the geometry. So in the geometry, we have seen the two example of centroid as well as the area. But there is far more applications which we can observe in the geometry. The two of other applications which I want to just say that mention over here is the reflection or the rotation. The reflection around x-axis and y-axis. So that this reflection kind of thing, this reflection operation or the process can be modeled in form of a matrix. So if you look at if you look at the reflection around or along this about the y-axis, so now I know that when you migrate from this quadrant to this quadrant, the value of y doesn't going to be changed. There is going to be change in the x value only. So here I am going to have the positive values, and in this case I am going to have the negative values. So the representation of xy after the reflection is going to be minus x minus y. So when you try to model this kind of reflection in a two-dimensional space, then of course this two-way matrix comes into the picture, where we are going to have the -1 as a coefficient over here and the +1 coefficient over here, so that every vector which is present in the first quadrant now is going to be in the second quadrant, and it is nothing but it will give you the reflection about y-axis. Similarly, if you want to take the reflection about x-axis, then again I'm looking for the reflection of this particular point in this particular quadrant, which is going to be somewhere over here. And I know that in this particular quadrant and this quadrant, the value of x won't change, the value of y is going to be changed. So basically this is going to be x minus y, and then immediately I can say the matrix is going to be this, which is going to be me the final way. Sorry, there is a mistake over here. This is going to be +1, this is going to be -y. So this particular matrix is going to be a matrix which is responsible for the reflection of these vectors over here. So this reflection, rotation, scaling, shearing, or what you can say, the affine transformation, these are all nothing but the pure applications of the linear algebra. And when you comes into the linear algebra point of view, the things are going to be much simpler, because you just need to multiply a matrix with a vector to get the new vector. Otherwise, then you have to do all the analysis and all the basic formulation you have to utilize. So basically, this is nothing but if I'm going to have a shape over here, then using the same matrix, I'm going to have the reflection of that particular shape about the x-axis or the y-axis, whatever it need to be. In the similar manner, now everyone knows about the rotation. It is going to be a very simple matrix over here. Like this is going to be the matrix, the rotation matrix usually called. Then you can plug in the different values of theta, and then you are going to have a different kind of outputs over here. So now everyone knows that there is this matrix is going to be very special matrix, uh, so especially in the sense this is going to be orthogonal, and the determinant of this matrix is going to be plus minus. So these are going to this rotation matrix is going to be very special matrix in the sense that it's going to be the orthogonal and the value is going to be plus minus one regardless of the values of theta. But this, as soon as you are going to have the different values of this theta, you are going to have different rotation in this particular plane. So now this, if I take this as my basic structure S over here, and then if I take a theta is equal to pi by 4, then or 45 degree, then this shape is going to be rotated, and you are going to get a new shape as star, where the structure is going to be the same. However, the position is going to be radially distorted. So this is all about the rotation. So even in the basic geometry concepts which we have learned, we can try to utilize the matrix concept of this linear algebra, and it is going to give you a very nice and comfortable way of doing things. Now this is again I'm taking a very simplest example now, because linear algebra is all about the solving the simultaneous equations. You can take any method, whether it is a direct method to solve a system Ax is equal to b, or it may be the indirect method or the iterative method. Every time you are going to have utilize the matrices. The simplest example is you have to represent your system in the matrix form, where you are going to have this matrix A, then this is going to be the vector of unknown, and this is going to be the vector of the right hand side of these equations. Then you are going to have X is equal to B, then you will find out the augmented matrix, you will apply the Gaussian elimination method, the Jacobi method, Gaussian. So different methods are going to be there, but all these methods are actually exploit the properties of matrices to get you a final answer. So let me take a very simple example. When you try to find out the augmented matrix, then using the pivoting, you just try to make these elements as 0 and these elements as 0. Basically, you just try to convert this into the upper triangular matrix over it, so that all the elements below the leading diagonal is going to be 0. And then using the backtracking, you are going to find out your solution. So this is going to be the way by which we are going to use the linear algebra to solve the different simultaneous equations. So why I'm taking this example over here is because when you talk about the real phenomena or the different applications in different engineering disciplines, so this is the technique or the process which is widely occurring over there, and the linear algebra is going to find its application there in that particular discipline. Because of this, the solution of the simultaneous equation. So in maybe in the classes to come, we are going to have certain examples of the engineering discipline as well, where the simultaneous equations are going to play a very vital role, vital role of solving things in a much easier way for them. So these are the very simple examples of the applications of linear algebra. So I think even if you don't have enough knowledge of linear algebra, you will be able to solve all these problems easily using the geometry, or you can say the basic mathematical understanding of the topic. Now let us try to talk about the different connections in the diverse area. So the first application which I will take in this set of lectures is going to be the image processing, which is going to be the straightforward, the next application I'm going to take. Then we will see the application of linear algebra in chemistry. Then the traffic flow. Basically, now I'm talking about the meaning of traffic flow is how the city management is going to find the application of linear algebra in devising the flow of the traffic on the roads. Then we are looking at from one application from the electrical engineering, basic the electrical circuits. Then graph theory. Then we will look for the security, and if the time permits, at the end we will look at the few applications of linear algebra in the machine learning and deep learning. Okay, so this is again going to, it is not going to be a very small list. It's going to be unending story for the linear algebra functions in the diverse domain and in the real life. So anyhow, if anyone want to ask anything, you may please ask in between. You can ask, you can stop me in between and you can ask. There is no issue. And Dilpreet, if there are a few questions in the chat box, you can also put those questions so that I can clarify those.
Okay, sure.
Yeah. Okay, so these are the different applications which I am intending to cover throughout this particular lecture series. So now the first application which I am going to take is image processing. I heard that you already have one lecture on the applications of linear algebra in image processing, but I'm going to give you a mathematical flavor to in order to exploit this particular relationship of linear algebra and the image processing. Let us try to have this particular journey of the image processing. So I am not including those stuff which you already covered in the previous lecture. So I'm trying to give you the distinct concepts which you have not done in that previous lecture. Okay, so just to start with the relationship of linear algebra and image processing, let me start with a very short mathematical story, which I hope you will like. So it's all about the Bunty and Bubbly. I think all of you are aware of Bunty and Bubbly. There is a very famous movie, Bunty and Bubbly, starring I think Abhishek Bachchan and Ravi Mukherjee. So let us talk about that particular Bunty and Bubbly. So assume that Bunty and Bubbly robs a bank, and then they have a Mercedes Benz with them, and they escapes in the Mercedes Benz. Now, since it's a robbery, case of the robbery, then police comes into the picture, and then the whole case is pursued by the police. Then after the persuasion by the police, we are going to have the two news. One is the good news, one is the bad news. The good news says that police took the photograph of this particular vehicle in which the Bunty and Bubbly are actually escaping. So they have the photograph of the number plate of this car. So now my assumption over here is this car belongs to those two people only. So that if we trace, if we use that number plate and try to trace the owner of this car, I'm assuming that we essentially going to get the Bunty and Bubbly. Now the bad news is whatever photo they have taken, that is blurred. Now what is the way out? So now what police did is they have taken, so that let me give a very small glimpse of that photo. So let's say that photograph is something like this, where nothing is visible on the number plate. So there is nothing is visible over here. So now what police did is police search for a mathematician. They take this photograph to the mathematician, and now and then they ask or they seek help from a mathematician that if mathematician can do in this in order to extract the information or the number of that particular car. So now what mathematician did is he will take that original image. So this is the image taken by the police, which is blurred in nature. So now I am saying that this image is nothing but a two-dimensional function. So within a moment we will see why I am saying image is going to be a two-dimensional function. So we will see that a very simple and elegant proof of this phenomena, why image is always going to be a matrix. So we will see that within a moment. But what mathematician did is he has taken that particular image, assume that is going to be a two-dimensional function. It is going to be, and he's taken in another image which is going to be very small image, and termed it as g of xy. He converts these two particular images to get an enhanced image h of xy, and using this enhanced image h of xy, he is able to extract the information of that particular vehicle. Now over here, this is the original image, this is going to be the enhanced image. Now what is this particular matrix? So this particular matrix is called the filter in the image processing point of view. Filter is nothing but a collection of some numbers which comes from a distribution. So now I have taken this picture over here. So now what you will do is, if you know that there is a blur into the image, you will try to identify what is the distribution of that particular blur. So now instead of linear algebra, now I'm getting into the probability instead. where you are going to have the different distribution, probabilistic distributions. So when you talk about image processing, it's all about the linear algebra and probability and statistics. So now I will try to find out, or I will try to estimate the distribution of the blur which is actually present in the original image, and using this distribution I will construct a matrix which is called the filter, such that when I apply this particular filter on the original image, whatever enhanced image I am going to get, that is going to have the desired output. So linear algebra gives the formula for a blurring. Of course, when I say the linear algebra, I'm basically mentioned about this particular matrix. However, the formula is basically derived from the distribution which you are going to receive from the estimation theory of the probability and statistics. So let's say this particular distribution is available, then of course I can construct this particular tiny matrix with me. Then I will just try to take the convolution of these two things. Since this is also a matrix, this is also a matrix, so it is nothing but the moving multiplication of a smaller image into the bigger image or bigger matrix. So then by inverting that particular formula, we can always get rid of the blur, and then we are going to have the enhanced information. So now this is a very visual thing which I am going to have over here. So now this is going to be the original image. So now you can see over here, nothing is actually visible over here. And when you try to find out the appropriate distribution, then try to construct a relevant matrix or filter. And when you convert the result, the output is something like this, which is responsible for unblurring the image. And then after doing this unblurring, I am able to identify what is the number of the bicultural PIKP606. So now this is going to be the image where the no blur is going to be there. So of course, in this case, since the scenario is such that the police is not able to take a very nice and clean photograph, even the mathematical concepts can do the better enhancement of that particular image, so that out of that particular blurred image, I'm going to have some meaningful information. So when you talk about image processing, except few concepts, everything is about the linear algebra. When I say linear algebra, specifically I'm talking about the matrices. So let me give a very brief summarization how the image processing is going to be related with the linear algebra. Then we will try to understand why image is going to be a matrix and how this two-dimensional function comes into the picture. So now let us take the image processing as a topic. Then when you deal with the image processing, you are going to have the different kind of scenarios over here. So the first scenario is how to represent an image. So now when you talk about the digital image processing, then the sensors will come, and then the cameras will come, and then they are going to have the different kind of technical terms over there, which will give you an image, digital image, which is in the form of a matrix. So we will again come back to that. So what is the image representation? So in image representation, when I talk about the image, then I talk about the pixel relationship, the distance between the two images, or maybe the two components of the images. Then what are the different operations, like can I add two images, can I subtract two images, can I multiply two images, can I divide two images, can I take the modulus of two images, something like that. And can we take the averaging, can we find out the median, can we take the kurtosis, can we find out the different elementary statistical properties out of that particular image. So all these things come under the category of the image representation. The next thing is the image transformation. So now I know that nowadays this smartphone market is very cheap. Now you are going to get the very good specification smartphone in a very less amount, and then everyone is going to have a smartphone, and then a smartphone can be used for taking the pictures or taking the selfies. So these pictures and selfies are nothing but going to be the images. And it may possible that while taking your selfie, the image is going to be a little bit tilted. And then you if I want to take the image of this particular object, and in the image the object is something like this. So it's going to be a rotated object in my image. So I want to take image like this, but I have taken the image like this. So where the actual object is going to be little bit tilted, then what you will do, then the easiest way out for me is I can go for the Photoshop or any other photo software, where I just try to rotate this particular image so that I'm going to have the same shape which I'm or in the form as I desire. So this is called the rotation of the image. Similarly, the size is very small, which you have taken from a camera, and you want to enlarge it, you can enlarge it. Or if the size is very large, if you have taken a very good quality of camera with you, then the size is going to be very large. And if you want to display it on a computer screen, then you may want to reduce the size. Then this resizing comes into the picture, and you want to just scale in and scale up your image. Then you can rotate image. Even you can rotate or you can crop the image. Let's say there are going to be two objects, and this object you doesn't want in your image. So you can always crop your image so that the interested or intended object are only present in the image. So these are called the different kind of image transformation which are involved. So I'm not taking a complete list. Even the shearing, wrapping, and other transformation will also come to the picture. So these are the most commonly used transformation which we have. Then we are going to have the image enhancement, and one example we have seen in the previous example of this continually. So now we are going to have the filtering, smoothing, sharpening, and there are going to be different ways to doing it. So when you try to reflect all these operations which I have listed in this particular table, then we are just looking at what is the mathematical interpretation of these things. And when you try to find out the mathematical interpretation of all these things, then the way out is going to be the linear algebra. So when you try to represent an image, you are talking about the introduction to the matrix. So when every image is going to be represented by a matrix, and all these relationship, distances, operations, averaging are nothing but the different matrix operation which you are aware of in the linear algebra. When we talk about the image transformation, it is again going to be the matrix transformation. It may be enlargement, reduction, translation, row column deletion. So all these particular operations or transformation which you might have in linear algebra will lead to the image transformations as well. Similarly, when you talk about the enhancement, it's all about the convolution or the multiplication of the original image with the different matrices. Of course, these matrices, there is going to be another way to find out these matrices, because you cannot just multiply your matrix with a random matrix and you are going to say that, okay, my image is going to be enhanced. If the due diligence is not followed, then you may even get a worse result than the original image. So these matrices has to be obtained after a careful analysis where the probability and statistics will play a major role, and this is going to be basically the estimation theory will tell you what is the nature of this particular matrix, and depending on the estimated values or parameters, you can immediately identify these matrices. So this is the very coherence, a very simple coherence between the image processing and linear algebra. So whatever you want to do in linear algebra, apart from few things, everything comes from the linear algebra point of view. So if you are very good in linear algebra, specifically the matrix theory, you can do wonders in the image processing. So now let me start the discussion why an image is always going to be a matrix. So now, in order to understand this phenomena, why image is always going to be a matrix, we need to understand one thing, that image is nothing but a function. Because when the orientation of a mathematician and the orientation of an engineer is going to be different, far different. Because an engineer is someone who take the existing concepts and apply it. They don't look at what is going inside that particular concept. They just try to find the similarity of a concept and their real world problem, and then they try to apply it. So it's a hidden trial kind of method which they are actually. But when you try to look at things from the mathematical point of view, then you are looking for the logical reasoning behind a particular thing. If I'm saying, why I'm saying all this, because if I say that image is going to be a matrix, then I should have a clear-cut proof of it. So let us try to have that particular discussion over here, where I am trying to say that image is going to be a function. So mathematically, when we talk about the mathematically, then mathematically an image is going to be a two-dimensional function. Let's say this is going to be the two-dimensional function where the domain is going to be the Cartesian product of two sets x and y. And after taking these any value from this particular set or this particular domain, it is mapped to a value from this particular interval 0 to n. So whenever you have this kind of function, then you are going to have f as a image function, or that is called the images. Where now let me say give what is the value of this L. So where L is going to be 2 to the power small l minus 1. So this L is a very is going to have a significance in this particular definition, which is going to get by which we are going to define the nature of that particular image. So this L is called the bits per pixel. Bits required for representing the image. So if I'm saying that in order to represent that image or a particular image, I am looking for only 4 bits. Then this small l is going to be 4 and this capital L is going to be 2 to the power 4 minus 1 and it is going to be 15. So the meaning is whatever representation I am looking at for a particular image, it certainly uses only the 15 symbols or the 15 values are going to be there. So this particular value of L, which is nothing but the bit representation or required for representing the image, will create this particular interval or the range, and this is called the dynamic range of a particular image. So this is called the dynamic range for that particular image. So this is nothing but the range for this particular function. But when you talk about the image processing, it is going to be the dynamic range of that particular image. So this particular L is going to define the nature of the image, and that is called the bit image. So whenever I take the 4 bits, that image is called the 4-bit image. When I take L is equal to 8, then it is called the 8-bit image. So the meaning is there are going to be required 8 bits to get the final image. And whenever you have only one implication of L, these images are called the grayscale images. Here, this 0 stands for the black color and this capital L stands for the white color. So basically, whatever dynamic range is going to be there, which is nothing but this particular interval, is essentially give you the shades in your image or in the photograph which you are going to have. Black is always going to 0 is always going to be black color, and this particular L is always going to be the white color which you are going to have. So this classification of L or different values which you are going to take for this L will define what kind of image you are going to have. For example, if I quickly take L as 1, then I am going to have L is equal to 1 only. So the meaning is I am going to have a uniform image. I don't have variations at all in my image. I'm going to have a single digit, and that is going to be either 0 or 1. If it is 0, then I'm going to have a black image. If it is going to be 1, then I'm going to have a white image. So depending on the application, you can always find out the value of L, and then depending on this value of L, you are going to get the different kind of images for your persona. So now let us take a very simple example how this particular kind of function will lead to a matrix. So let me take a very simple example. So now, as I mentioned that this function, again, if you look at this, is going to be a 2 set. So one element come from this set, one element come from this set. So basically, I'm looking for the Cartesian product of these 2 sets. So I'm going to have a double kind of thing over here. So now I am working with the 2 independent directions. So this is going to be a 2-dimensional function. So if I'm saying that image is always going to be a 2-dimensional function, then meaning is if I'm going to have a two-dimensional function in mathematics, that should also lead to an image. So let me take a very simple example of x plus y. So now the question comes is construct an image of size 2 by 2 using the two-dimensional function x plus y. So now we will try to see how this 2 by 2 image is going to be lead to a matrix. So of course the definition of x is given to me, but now in order to get the final output like values from 0 to L, what I'm looking at my set x and my set y. So now let me take my set x is going to have only two elements 0 and 1. Y is again going to have two elements 0 and so both the sets are going to be same x and y. So whenever you try to have the linear the Cartesian product of this x and y, so can anyone tell me what are the elements over here? So it is nothing but the combination of all these elements. So this 0 will go with either this 0 or this one. So it is going to be element 0, 0, 0, 1, 1, 0, and 1, 1. So the meaning is if I'm trying to construct a 2 by 2 matrix or 2 by 2 image using this particular two-dimensional function, then this is going to be my domain. So I will pick any element of it, plug in over here, and I'm going to get some value. So let me try to do that exercise very easily. So f00 is going to be, so in this case, this f00 is going to be 0 because it's nothing but x plus y. Similarly, if I take f01 is going to be 1, f10 is again going to be 1, and f11 is going to be 2. So I am going to have the 4 elements in my domain, and with respect to these 4 elements, I am going to get this particular value, and hence the dynamic range for the image to be considered is going to be the interval 0 to 2. Some book says that instead of taking this set or the interval, you can always take a set. So some books say that instead of taking this, you just take the set after the collection of 2. But now there is an issue because the repetition is generally not allowed in sets. So now it may be possible that you are going to have repetition. So just to avoid all those things, I will say these values comes from this particular range, and hence the interval comes into the picture. So that this repetition can be taken care of. So now what is happening? Now you are going to have the two independent direction. So let me say this is going to be the independent direction x, this is going to be my independent direction y. What are the possible values of x? I'm going to have the 0, 1. What is the possible values of y? Again, this is going to be 0 to 1. Now, when I take the linear, when I take this particular element 0, 0, I am going to get a value 0. When I take 0, 1, I am going to take, let me take this my x and this my y for the simplicity. So 0, 1, whenever I take 0, 1, this is going to be 1, this is going to be 1, and this is going to be 2. So this is nothing but the grid for the function values. For function values. So now this is going to be grid, and whenever you try to represent a grid, the only way out is you have to have a matrix into the picture, and hence when you do all this analysis, you are going to get a 2 by 2 matrix or 2 by 2 grid having the 4 elements 0, 1, 1, 2, which is easily represented by the concept of matrices, which is nothing but 0, 1, 1, and 2. And hence the 2 by 2 image with respect to this function is given by this particular matrix, and so hence this is going to be the image. So now when we try to do the image processing, it's going to be inverse form. Right now what I did is I have taken a 2-dimensional function and then tried to find out the image. However, when we are having an image in our hand or a photograph in our hand, we are standing at this particular location and we don't have the information of f of xy. And all image processing is all about to find out different ways by which we can identify this f of xy, or maybe not the the exact one, maybe the approximate, because it is going to be imposed problem, because using these four values you have to give this particular function. So in most of the times it's going to be imposed problem, and hence you are not going to get a unique answer to it. But you just try to find out the approximate function f of xy which is associated with a particular function. But this particular whole discussion or analysis will tell you one thing, that doesn't matter how I am acquiring a particular image. If I am taking an image, whether it is going to be from the webcam, from the smartphone, from the camera, or anywhere else, what I am going to have a matrix. Now, so this particular matrix is always going to represent an image which you might have taken from any of the source. Now, what are these values? So these values are called the pixels of the image. So this is nothing but the pixel. And hence, in the technical terms, I can say that an image is nothing but a collection of pixels. So every image is going to be the collection of pixels, and this number of pixels is going to define the size of your image. So if I'm saying that I am going to have an image of some scene, let's say of size 200 by 100, sorry, 100 by 200, otherwise it is not going to match with the structure of this. So 100 by 200, the meaning is then the collection which I'm going to have of these pixels or of these function values or the image function values are going to be the multiplication of these two. So I'm going to have 20,000 pixels present in that particular image. So every image is going to be represented by a matrix, and the entries of the matrix is going to have are going to call the pixels, and this is going to be a particular values corresponding to a function that is called the image. So this is how the image concepts comes into the picture, and then using the reverse engineering, we are going to find this particular function for different purpose. Like that, if I want to enhance my image, I should be aware of this function f of xy, so that mathematically I can do those kind of enhancement for different kind of. So I hope that is it clear to everyone why an image is always going to be a two-dimensional function, and how this two-dimensional function will lead to a matrix. So I will take a pause of 2 minutes, so that if you have some query so far, which whatever we have learned, you can now ask those queries with me. So that we are going to have a discussion on those queries. So Dilpreet, is there any query in the chat box?
Let me see. Okay.
Okay, so I think let me open this forum for a quick discussion. If someone is going to ask something regarding anything, whatever we have done so far, so you are most welcome. You can unmute yourself, and then you can try to talk to me, and then I will try to clarify your doubts. In case of you don't have any query, then let us extend the concept of this image processing further. So anyone who want to ask something, or should we proceed further?
I want to know.
I think Vijay Kumar is asking something. Vijay, can you please repeat your question?
Sir, as in this example, we have taken x and y as a discrete set, okay?
Your voice is very low. I think you are asking that why I have chosen x as 0, 1 and y as 0, 1.
No. Am I audible,
Okay.
sir, clearly?
Pardon?
Am I audible?
Now you are audible. Yes.
Yeah. Sir, I am asking you that you have taken x and y as a discrete set, okay? 0, 1, 0, 1.
Yes.
And using the function f of xy is equal to x plus y, you have got that matrix 0.
Yes, I got this matrix.
Then
yes.
how can it create a continuous picture? What about the intermediate
No,
point?
picture is not going to be continuous at all.
No,
When
sir,
you talk about image is always going to be discrete.
discrete, but sir, when we see the outputs, we are having uh, all the gaps in between are filled up.
Okay, so that is actually due to the large volume of pixels. So
Okay.
you do one experiment. Maybe if you have a photograph in your smartphone, just open that photograph and try to zoom in. Zoom
Yeah,
at the maximum level.
maximum level.
When you
Then
try
that
to
time
zoom,
we can see the
yes,
pixels.
that is not a pixel, that is the blocks. So that is called
Yeah.
the pixels at a particular location. So no image is going to be continuous in nature. Since
Yeah.
your number of pixels are very high with respect to your screen in which you are looking at your image, you feel that the image is continuous. But
So it makes
in
us to feel that
actual
yeah,
manner, it is
image is
always going to be
continuous.
discrete. Pardon?
Okay, sir. Yeah,
So
that number of pictures makes us to feel that yeah, the pictures is
it's a continuous
continuous.
image. Yes, it's a continuous.
Okay.
But no
Okay.
picture is going to be continuous because
Okay.
every picture is represented by a matrix, and matrix is going to be a discrete structure. It is not going to be a continuous structure at all.
Okay. Okay, sir. Okay. Thank
The
you.
transformation which is going to utilize the matrix, that may be continuous, but matrix itself is always going to be discrete because it's a collection of different elements.
Okay, sir. Thank
So,
you.
but your question is prompting me to say a few things about this x and y, because uh, you have said that why I have taken this 0 and 1. Even you can take an interval, no issues in that. So now let me take a very simple example just to try to extend this concept why I have taken this discrete in nature. Let me take my x as the interval 0 to 1. Let me take y as also as 0 to 1. So now this is the interval. So how many elements are there in the interval? That is my question. So between 0 to 1, you are going to have the infinite numbers. You have
Yes,
infinite
sir.
numbers. So you are going to have the rational numbers, irrational numbers, everything all together. You are going to have the infinite values in this particular interval. Similarly, in this particular interval as well. But when you try to find out an image, the size is going to be the fixed.
Yeah.
For this example, I said that I am looking for 2 by 2 image only. I may also say that I am looking for 4 by 4 image only. So this function will also give me a 4 by 4 image, 8 by 8 image, or let's say 100 by 100 image. But what I
Oh.
am trying to do is, out of this infinite values, I need to pick certain values, preferably in the equidistant manner, such that I am going to create the desired size of that particular image. Like if I say 2 by 2, so the obvious choice for me is 0 and 1 for x as well as for y. If I say I want to construct a 4 by 4 image out of this particular function, the meaning is if my x is going to be 0 to 1, then in this particular interval, I am looking for 4 values. And then those 4 values are again going to be very obvious choice for me. So you
Yes.
will take 0, 0 0.25, 0.5, or maybe 0.75. Again, these are the different values which are going to be equidistant and lying in this particular interval. Someone may start from 0.25 and go till 1. So it's all about your perception and how you are going to choose those values. So of course I agree. When I say x cross y, then this set x and y are maybe interval. But in order to make an image of definite size, I am going to take those are sets. And whenever you are going to have this kind of phenomena, which is going to have an interval or the continuous set, and out of this you are pulling up some value, this concept is called the sampling.
Yes, sir. Sampling. That means
So
you
this is
collect the
also the
data.
sampling theory. So
Yes.
you can take this x as the continuous, y as the continuous interval on the whole domain, whatever domain you want to take, you can take, and then you can using some criteria you can pick up the different values, and this actually comes under the category of sampling theory, where you
Samples.
have to satisfy the
Use
Nyquist rate for the
yes,
better
Nyquist
sampling of the
rates.
points. So
That I
I'm
have done, sir,
not
in
going
signal
in that
processing.
particular. Vijay, can you please repeat what you are saying?
That I have done in signal processing,
Yeah,
like
everything
to
is same.
space.
Everything is same.
Yeah,
Signal, when you talk about signals, signals are always vectors.
vectors. Yes.
Okay, when you try to extend from signals to image, that is going to be matrix. So it's a very simple extension of a number to a vector and then vector to matrix. So whenever you are in the vector domain, you are working with the signals, one-dimensional signals. And whenever you are in the matrix domain, you are with the image. But the underlying philosophy of the sampling is going to be same. So, but again, in this lecture series, I'm not actually discussing this sampling. But if there are requests, then I may try to see at the end. We may have a full lecture on the sampling as well. So now the next question which you may ask is this interval about this interval 0 to L. So in this case, I am saying that my L is going to be 2. But L is not going to satisfy that criteria. It may possible that for some function f of x, y, L cannot be in the form of 2 to the power L minus. You cannot try to reflect that. So then you are trying to make everything or whatever numbers you are going to get in a certain interval depending on this small L, and that process is called the quantization. So whenever you try to construct an image, it is just the application of the sampling and the quantization for different purposes. Sampling will define the grid or the size of the image. Quantization will decide the pixel values which you are going to have for a given image. So whenever you combine all together, you are going to get a very nice and clean image. And if the size is pretty large, then you will not even notice that you are looking at a discrete entity. You will feel that it's going to be a continuous entity. So whenever you try to enlarge those images, then you are trying to visualize that, okay, no, I am still looking for the discrete images rather than the continuous. Okay, so any other question from anyone? I think someone has written something in chat box. So what's the motivation that image is defined like this particular type of 2D functions? I think Aritra Roy is asking this question. So basically, when you talk about the images, and the motivation for this is ultimately when you try to capture an image, you have to store somewhere, and the most of the time the storage device is going to be a computer or a smartphone, which is again going to be a very compact size of computer only. So whenever you talk about computer doesn't take the continuous things. Computer always work with the discrete things. That to basically the binary number system, but everything has to be a discrete. You cannot plug in the, for the simplest example, if let's say in the C++ program or any of the programming, if I want to fetch the value of pi, let me take here the value of pi, I know that is going to be 3.14 and so on so on. So it's going to be a recurring number again and again. So I don't have an ending over here. However, I cannot give this kind of number in the computer. I cannot fetch this kind of number. So the meaning is, if I cannot fetch this number, then I am looking for an approximate number. So then this whole continuous process has to be discretized at some point of time. Then I have to decide, okay, how many decimal places I am going to require for a particular problem, so that the desired accuracy level is going to be achieved. And that desired accuracy level will decide how many decimal points you need to take. So for simplicity, I'm just taking a 2 decimal place. So most of the times we are going to take 3.14 as the value of pi. But this is not the actual value of pi. This is the approximate value of pi. The actual value has more digits after this 4. So just to feed this information into the computer, I need to discretize. I need to take a call that, okay, if I want to use this in my computer, I need to truncate it at some point of time, and that truncation will lead to a discrete process. Now, the same scenario is there for the images. If you want to take the image and store into the computer doesn't work on the continuous things. You have to make the process discrete in nature, and a rectangular discrete arrangement is always a matrix, and that is why every image is going to be a matrix, maybe square or maybe rectangular. So this is the only motivation, that if we are capturing some image, that image has to be for the storage purposes, and I need to store that. Even if you look at, if you want to take the printing of that image, nowadays the printer are also working on the digital domain. So again, you need to take a digital image for the printing. So now there is no printer which will give you the printing of a continuous image. So everything has to be digitalized. So in that particular sense, you are looking for the discrete domain only, and hence you have to define your image in this particular manner. Anitra, I hope that I have clarified your query.
Yes, sir. Yes.
Okay, so now let us further extend this concept of images, because I mentioned in the last slide that
See,
yeah,
there is one question from Usha. She is asking about the color of the image, sir.
yeah, ma'am, please hold on your emotions for a second. I'm just trying to extend for the grayscale to the color images. There's the next slide for today's lecture. So within a second, I will give the answer. What is the meaning of color images? So as I mentioned that in this particular slide, I said that whenever I'm going to have the function under this particular setup, I am going to get a grayscale. But when you try to take photographs for your mobile or for the maybe the current cameras, you are going to get not the grayscale image where only the black and white and the different shades from there, gray shades are going to be there. You are going to have the different colors. Yeah, you are going to have the red color, blue color, green color, magenta, and all those colors are going to be there. So now what we will do, so that this 2D function, which is going to give the grayscale image, is going to give us the color image. So now next is the color images. So color images is the simple extension of the grayscale images. What we are trying to do over here is, we are instead of taking one function f, now we are going to take the three different functions r, g, and b. So this is the function with respect to the red color. This is the function which is going to set the green color, and this is the function which is going to contribute toward the blue color. So whenever you are going to take this vector arrangement of three different function values, where the first value is going to towards the red color, second value towards the green color, and third value towards the blue color, and when you take the combination of these three, the appearance will look like a color image. So basically, it's a very simplest extension of matrices to the tensor where you are going to have the three values. So in this case, what I'm going to have, I am going to have one image with respect to R, another image with respect to G, and the third image with respect to B. So now it's going to be a collection of matrices. So color image is nothing but the mere extension of the matrix theory, where you just want to take the collection of different matrices. So there are different kind of models which we are going to have. The widely used method is called the Rgb model, where the three function will represent the red color, green color, and blue color. And whenever you are going to overlay these three values or these three matrices on each other, you are going to get a color image. So this is the basic definition of color image. And here R, G, and B are the same function and built on the same philosophy which we have seen for the grayscale images. So color image is again going to be image function, but here you are going to have the three different components. So everything now is going to be in the vector form. So color image is nothing but the combination of vector as well as matrices. So again, as I mentioned that in this three colors are going to R, G, and we have integer values from 0 to 50. Again, this 255 will come when I will take small l is equal to 8. So this is the widely used setup for all the images. So they will take the small value of L as 8. So the capital L will come 2 to the power L minus 1 or 2 to the power 8 minus 1. When you solve it, you will get the value at 255. So their dynamic range is going to be 0 to 255. So most of the current devices are going to work on this particular setup of L is equal to 8. So they are going to represent every pixel with the help of the 8 bits. And this has to be true for all R, G, and B, for all the three colors. And then when you combine these, then you are going to have a color. So you can look at it, since we are going to have the 256 value for all, 256 value for G, and 256 value for B. And all together you are going to have this much color combination which you are going to have in the current scenario, and these combination will lead to the color images. So Usha, have I answered your query? How the extension of the color images from the grayscale image is going to happen? So mathematically is nothing but the collection of matrices, and different models are going to have the different values to consider. Okay, so let me give you very brief idea of two very famous models of color images. One is the RGB model, where I am going to have the image of the same object from the perspective of red color, from the perspective of green color, and from the perspective of blue color. And whenever I overlay these, I am going to get a well-defined color images which we are going to have nowadays in our hand, in our smartphone, in our cameras, or in our laptop. The another model which is going to be there is called the Cmyk model, where the color models we have to consider is cyan, magenta, yellow, and black. And whenever you try to overlay these images, you are going to get the image which is called the color image. So now whenever you talk about black, so this black is nothing but the grayscale, which you are going to have in the previous case. So this is nothing but these three colors along with the grayscale version of that particular object will give you a color image. So this is all about the color image. But now I think in order to get the more idea about this color, how colors and the linear algebra is going to be attached with each other. So let us have a very quick discussion on the colors and the linear algebra. So linear algebra and colors. So now the linear algebra is also tightly associated with the colors, which you are going to see around you. So let us have a very quick example of it. So now I am now trying to consider the Rgb model of color. So whenever you have a Rgb model, so this model, the underlying philosophy says is this red, green, and blue are going to be my primary colors. So I will assume that the rest of the colors which are not covered by these three colors are going to be the linear combination of these three colors. So this particular figure will give you an idea how things will move over here. So this is going to be the red block, this is going to be blue, and this is going to be green. When you just combine the blue and red, you are going to get the magenta color. So I know that if any one of you is going to be a good painter, then you are going to appreciate more, because you are going to have a better sense of forming the new colors out of the existing colors. So if you look at these watercolors, which usually children are going to have, they are going to be the limited number of colors only. And despite of that fact, they are able to construct all the possible colors after mixing different colors all together. So it's all about the mixing of the primary colors which we are going to have in our hand. So in this RGB model, we will assume that we are going to have only three colors in our hand, R, G, and B. So now you can always try to relate this fact with the color printer. So whenever you are going to have the color printer with you, there are going to be four categories. One is black, and then you are going to have the three different colors. So the meaning is that printer won't work on the RGB model. It actually work on Cmyk model, where one is going to be the black cartridge, and then three are going to be three different colors, the cyan, magenta, and yellow. And when you try to combine these colors, you are going to have all the spectrum covered for the colors. So that is called the Cmyk model. So again, I'm not going to discuss Cmyk model because the philosophy is going to be same as we are going to have in the RGB model. So you can visualize those things very easily. So now whenever I try to just mix the blue and red, the color which I'm going to get is magenta. Similarly, when I just try to mix the blue and green, I'm going to get the color cyan. And whenever I try to mix green and red, I'm going to get the color yellow. And now I'm going to try to mix the third color as well. So when red, green, and blue are actually mixing, I am going to get the white. So now, here the underlying philosophy is the percentage of blue color and red color are going to be same. But it is not always a case. It may be possible that out of this primary color, I may I may give weightage to a certain color. Like if I'm going to, in this case, the thing is 100% blue and 100% red, you will get magenta. But it may possible that I will take only the 50% of blue and let's say 100% of red. So of course, I am not going to get a magenta. I am going to get a variant of magenta which is close to the red because the dominant color is going to be red. So now different percentage of these color will give you the different kind of colors. So this is all about the linear algebra and colors. So let me quickly go ahead. So now since I am saying this RGB model, this red, green and blue color are going to be the primary color. So I'm going to represent this in a three-dimensional space where one axis is R, G and B. And then this one is nothing but the percentage. So one is representing 100% of this. So whenever you are having these two terms as 0, you are in the pure red and so on. So whenever you are trying to have the different combination, you are going to get this particular color cube, and this color cube is going to have all the combinations of all the colors. So let me give you an example how the things are going to be moved. So how the linear algebra comes into the picture. So any color seen in that particular cube which we have seen in the previous slide can be represented as a system of simultaneous equations, or the system of this equation C is equal to AX, where A is nothing but the collection of your primary colors and X is nothing but the percentage to those primary colors. So like if I'm in this case, my primary color is R, G and B. So this is the R, G and B. The column of this matrix is R, G and B. And these are the percentage associated with these particular colors. So because if you take the multiplication of this, you are going to get nothing but the linear combination of these colors. So different values of this x1, x2, x3 will give you different colors altogether. So let me take a very simple example. When I take x2 and x3 as 0 and x1 is 1. So in this case, there is no contribution of blue and green color. So the output is going to be a pure red color. And then you can see that I am going to deviate from the red color when I am mixing either the blue color or the green color. Then and only then I am deviating from the red color. Otherwise, I am in the pure red color. So whenever these two values are 0, I am going to have these two values are going to 0. I am going to have pure red color. Similarly, now I can change the value. So let me take this x1 and x3 as 0 and x2 as 1, and this is for the green color. Hence, the output is going to be the purely green color, because I am not mixing any of the primary color with the green color. In the similar way, now let us take an example when we are going to have these two component x2 and x3 as x2 and x3 is going to be 1 and this is going to be 0. And in this case, I know that now I am mixing the green with blue. So from this figure, I know that when I mix green with blue, I am going to get a cyan color. So I am going to get the cyan color. So now let me end today's lecture with a question. What is the percentage of x1 and x2, x1, x2 and x3 if I am going to get this color? So this is not the blue. This is something kind of navy blue. So what are the possible percentage or the possible values of this x1, x2 and x3 so that I will get this particular color? So can anyone give me an idea? What are the values of x1, x2 and x3? Anyone want to take a try?
x1 is 0.4, x2 is 0.4 and x3 is 0.8.
0.4, x3 is 0.8. Okay, what about x2?
0.4.
So you are taking 0.4, 0.4, 0.8. Is it correct?
Yes, sir.
Okay. So why you have given 0.8? But first let me ask this.
Because I want variant in the color of blue.
Yes.
That's why.
So now just try to compare this output color with the primary color. So I know that this color is close towards this particular color red. And again, if you look at very clearly, the variation is not too much. And hence I can deduce that the percentage of blue color is going to be maximum and the percentage for these two colors are going to be minimum. So this
minimum.
can be one of the solution, but this is not the exact solution which I have taken. So if you look at my observation, so I have taken the 50% of red color, 25% of the green color, and then 100% is going to be the blue color. So, but again, this 40%, 40%, and 80% is again going to be one of the solution, because again the dominant color is going to be this. However, this color is I have created with this particular combination. So now, just comparing your output color with the primary color, you can try to, you can visualize very easily that which is going to be the dominant color and which is going to be the non-dominant color in order to creation of this particular thing. And then you can try the different kind of possible values of x1 and x2 and x3 to get the final solution. So now this problem is going to be very ill-posed problem, which you can easily understand, because if I'm saying the 50, 25, 100, if I just change this value as 50, 25, or let's say 98, this combination will not going to be far different from this color. So it is going to be the approximately same. So the meaning is, the problem when you are going to have a single output and you are going to get the percentage of three different primary colors or more than one primary colors, then this particular problem is always going to be the ill-posed problem, because you are going to have the less given information and looking for the more information to be found out. So it is going to be the ill-posed problem, and which is going to be very hard to solve, and hence it is going to be a hit and trial kind of method. You will try to take the different values of x1, x2, and x3 until you are going to get the desired color which you are going to have. So now I will stop today's lecture with a very simple explanation of the cube. As I mentioned in the previous slide, that whenever you are going to take the different combination of these three primary color, you are going to have the complete spectrum of your color. So if you look at that particular, if you recall that particular cube which we have seen along with this particular figure, so it is going to be something like this. So this is going to be the cube. This is going to be the white color. This axis is going to be the red color. This axis is going to be the green color, and this axis is going to be the blue color. And then when you take the different combination, you are going to have the complete spectrum of all the colors of all the colors. So the sides which are not visible in this figure are given below this particular cube. So now you can look at arranging from black to white, blue to pink, red to yellow, green to yellow, every color which you can think of, you can now try to you can have access to those colors. The only thing which you need to understand is, what are the percentage I am going to take for these three different colors to actually form that particular desired color, or to form this particular spectrum. So these colors are nothing but the linear combination of the basis color of the primary color, which you can understand, which you can assume in a certain model. Like in Rgb model, R, G, and B are the primary color. Now you can have the Cmyk, where you can have the cyan, magenta, yellow, and black is going to be primary color. So in any of the case, any of the model, you just try to take the linear combination of the different colors which you are going to have to produce all the colors. And whenever you try to overlay these things in form of a tensor, then you are going to have the color images into the existence. So I think the time is over for today's lecture. So I will stop here for today's lecture. In the next class, we will try to see the two very famous factorization technique of linear algebra, which have the widely used in the image processing and other areas such as the data science, artificial intelligence, and machine learning. And those are the singular value decomposition and the principal component analysis. And then we will try to have a discussion how this SVD comes into the picture, what are the benefits and all those things we will see in the next lecture. So again, now I am putting the floor for the questionnaire. If you are having some queries, some issues, you can now discuss it with me, so that we are going to, I will try to clarify your doubts. So I will now stop sharing my screen. So now we are going to have a discussion on that particular thing. Okay, so queries from your side.
So Sir, please suggest first course book in this image processing with mathematical approach.
So there is a very famous book by Anil K. Jain. So you can search that particular book. I somehow forget the name of that book, but you can search the digital image processing by the Anil K. Jain. You will find that book. So that book is a very fundamental book in the image processing, and then you will have the mathematical flavor to it. But
Thank you, sir.
again, try to use that book when you are going to have a better understanding, very good understanding of linear algebra. Otherwise, you may miss out in between. If you want a very basic book of the image processing, then there is a book by Digital Image Processing by Gonzalez and Woods. So just take either the first edition of it or the sixth edition of it. So the first edition and the sixth edition of this book is completely full of mathematics, but the intermediate versions are actually lacking in the mathematic point of view of the image processing. So any book you can follow. So this Gonzalez and Wood book is going to be very basic. It is written in a very basic, very basic English and everything. So everything is as you can appreciate that book. But if you are very strong in linear algebra, then I will suggest you to go with the AK channel. Yes, this is the one. This Fundamentals of Digital Image Processing by Anil Kumar Jain. So you can consult with these books. So any further queries? So Dilpreet, I guess there are no further queries. So maybe we can call off today's lecture. Then we will meet tomorrow.
Thank you very much. Thank you very much, Dr. Bhatnagar, for this lecture. And before I end this session, I have a couple of announcements. So the first is I have sent feedback form for this program to all of you. So I request all of you to fill that form by Sunday, that is December 13th. I will also share one more form for feedback on instructors and tutors, maybe tomorrow. You have to, it's compulsory to fill both the forms as per rules of NCM. The second announcement is the second lecture of this series will be taken tomorrow at 5:30 p.m. by Dr. Gaurav Bhatnagar. Okay. Okay, so that's it.
Thank you, everyone.
Thank you, sir. Thank you very much. Okay, this meeting now.
Yes. Okay,
Thank you.
thank you, everyone, and have a good night to all of you.
Okay, bye. See you tomorrow.
Yeah.
So please fill those